Okay, this last lesson for chapter 6 is partial fraction decomposition, and it does not relate to systems at all, so it's a little bit kind of different from what we've been doing, but a nice little break nonetheless. So what this does is it uses systems of linear equations to decompose rational expressions into the sum of simpler rational expressions, specifically into quadratic or linear factors. So I guess that's the way it connects the systems of equations. However, most of it kind of feels a little different. So this process will be useful in calculus, where simple rational expressions are often preferred, and here's what we're hoping to achieve. So you'll notice here on the left side, you've got that denominator that says x to the fourth plus x squared, and then we break it up into simpler denominators on the right. So if we're given an expression on the right side of the equation, it is the matter of intermediate algebra to determine the common denominator to obtain the expression on the left. The focus of this section is to develop a method which we start with the expression on the left side and resolve it into the partial fractions to obtain the expression on the right side. Essentially, we want to reverse the least common denominator process. So there's some different cases. The first case we're going to look at is for something that's non-repeated linear factors, meaning each linear factor is unique. So let's go ahead and dive in, and you'll notice over there on the right it gives you some steps. So to find the partial fraction decomposition for non-repeated linear factors, the process on the right is always the same. So create an equation by setting the original equation equal to the appropriate of sum of partial fractions. So the first thing I'm going to do, and that I recommend doing even before that, is let's just factor the denominator there. So the 5x plus 16 is going to remain the same, but what multiplies to 24 and adds to 10? You would have 6 and 4. So x plus 6, x plus 4. So your two linear factors are the x plus 6 and the x plus 4. And we're going to add those. And then notice what we have up top here in this yellowish is we've got just an a and a b. So some constant a and b that we're going to solve for. So we have rewritten as the sum of partial fractions. Okay, so now we're going to multiply both sides by the equation by the least common denominator. So if you multiply by this x plus 6 times x plus 4, this and this will cancel, but we also have to do the same over here on the right. I've got to apply that whole part. So 5x plus 16 on this left side. When you do the x plus 6 times x plus 4 times the a over x plus 6, the x plus 6 and the x plus 6 will cancel. So you'll be left with the a times x plus 4. Same thing here with the b over x plus 4 times x plus 6 times x plus 4. The x plus 4 will cancel, and you'll be left with b plus b times x plus 6. Okay, now we're going to distribute. So we get 5x plus 16 equals ax plus 4a plus bx plus 6b. So we expanded the right side of the equation. We're now going to collect the like terms, like step 3 says there. So the left side still stays the same, but we're going to have ax plus bx together, and we're going to have the 4a plus 6b together. And I'm going to take this one step further so that it looks really similar to what we have on the left. I'm actually going to factor out an x term from that, so we'll have a plus b times x plus this 4a plus 6b. I'm going to put that part in parentheses too, because I think it will help you see step 4. Step 4 says equate the coefficients on the left side to the terms on the right side. So you'll notice here, if this is really equal, this is the coefficient of x, but so is this. So if those are the only x's, then 5 must equal a plus b. Similarly, if we look at the constant, we've got a constant of 16 here on the left, and on this side we have 4a plus 6b. Now it's up to you how you want to solve the system of equations. I probably am going to do elimination, but there's multiple different methods, so maybe I eliminate the a's and I multiply this by a -4. So I get -20 equals -4a minus 4b. Add them together. We get -4 equals 2b, so b equals a -2. And then we got to find a as well. So we would do 5 equals a plus a -2. Add 2 to both sides, so a equals 7. So now that we have the constants, we're going to use those constants to rewrite our partial fractions. So the answer would be 7 over 6 plus x plus 6 plus a -2, or you could do -2 if you wanted it, over x plus 4. And that's a way to rewrite the fraction 5x plus 16 over x squared plus 10x plus 24. Okay, now let's look at what we're going to do if we've got repeated linear factors. So notice here, if you look at the denominator, we've got x plus 3 squared, right? So really you can think about that as being, if it helps you, like x plus 3 times x plus 3. So you see how that's repeated? It's the same linear factor of x plus 3. So what they say here, if you look up in the box, that kind of tells you how to break it down. The left side, right, doesn't usually change, x plus 3 squared. But the way that we write the right side is we write the first linear factor, and then we add the second linear factor, which is the same number, but then we're going to add a squared. If it was x plus 3 cubed, we'd write one more plus something over x plus 3 cubed. On the top here, you're still going to have just a constant. So since these are both linear, even if it's a repeated one, so it looks like it's quadratic, you're still going to have a constant on top. Okay, same steps as before, multiply both sides by that denominator. So this cancels, we're left with 7x plus 14. A over x plus 3 times, maybe it helps to write this like here too so you kind of remember. The squared will cancel with that, so it'd be a times x plus 3. And then these would just cancel, so you'll have plus b. So let's simplify the right and kind of combine our like terms. So we'd have ax plus 3a plus b. So this time we've got just one number in front of x, so the 7 and the a have to be equal, so 7 equals a. And then we look at the coefficient, so the constant, 14, equals the 3a plus b. But we know that a is 7, so 3 times 7 plus b. So 14 equals 21 plus b. So b equals a -7. Now all you do is write your answer. So we're going to put 7 over x plus 3 plus -7, or you could do -7 if you wanted, over x plus 3 squared. Okay. So now it gets a little more complicated when you've got quadratics. So anytime you've got a quadratic on the bottom, you're going to put a linear factor. So you'll notice you've got like an ax plus b on the top. So think about your numerator is 1 degree less than your denominator. So linear, you'll put a constant on the top. A quadratic, you'll put a linear on the top. So the left side won't change at all. And lucky for us, the denominator is already factored, so we've got a linear. But then this x squared plus 6x plus 1, there's something that multiplies to 1 and adds to 6. We can't break down that quadratic into two linears. So our two different ones is going to be this x plus 3, and the second one's going to be the x squared plus 6x plus 1. So with the linear, x plus 3, we're going to just put a constant a on top. But with the quadratic, we put a linear, so bx plus c. And we're going to try to find a, b, and c. So we start by multiplying by the denominator here. So those cancel out. Got to do the same here though, right? So those would cancel. We'd be left with a times x squared plus 6x plus 1 do the same over here. These would cancel, be left with bx plus c times x plus 3. Here, I would make sure to also put that bx plus c in parentheses, otherwise you may forget to distribute. We've got 4x squared plus 17x minus 1 on the left still. Okay, so on the right here, we're going to have to multiply and combine like terms. So we get ax squared plus 6ax plus a plus bx squared, whether you do the box or you distribute up to you, plus 3bx plus cx plus 3c. Okay, so now let's make sure to kind of group together our x squareds and our x and our constant. So here we have two x squared terms, so I'm going to just do that as a plus b times x squared. I kind of combined two steps, so I factor out the x squared there too. I've got three x terms, so I've got 6a plus 3b plus c all times x. And then I've got plus a plus 3c as our constant. So we now are going to equate the coefficients on the left with what we have on the right. So in front of our x squared term, right, we've got 4 and we've got an a plus b. So 4 equals a plus b. Then for our x, we've got 17 and we've got the 6a plus 3b plus c on the right. And last but not least, we've got -1 equals a plus 3c. Okay, let's try to now solve the system of equations. So, I mean, you could use something like a matrix here if you wanted. You could use Cramer's rule, their determinants, or you could just use like our elimination like we did to begin with. I'm going to go with elimination because I think that's what you guys are most comfortable with. I'm going to try to eliminate the c. So if I do that, in the second equation, I'm going to multiply by -3, and then I'm going to add those two equations together such that I just have a and b and combine it with the beginning one. So -3 times 17 is -51 equals -18a minus 9b minus 3c. So then I get -52 equals -17a minus 9b, and then your c's cancel. Okay, I'm now going to use that along with the top equation. So that top equation, I'm going to multiply by, let's have the a's cancel. So let's multiply by 17. 17 times 4 is 68 equals 17a plus 17b. So we'd be left with 16 equals 8b, which means b equals 2. Once you've got that, it's now just plugging things back in. So if I've got b equals 2, then I could do 4 equals a plus 2. So a also equals 2. And then I'm going to do the last one. So -1 equals 2 plus 3c. -3 equals 3c. c equals -1. So you'd be left with a is 2 over x plus 3 plus b is 2x minus c, or add c, so -1 over x squared plus 6x plus 1. Okay, so similar to what we did kind of previously, we can also have repeated linear factors. So the first thing I'd always look at is, hey, can we break down the denominator? So in this case, our numerator will stay the same, but our denominator is going to be, notice how this almost looks like x squared plus 6x plus 9. So it multiplies to 9 and adds to 6, 3 and 3. But rather than this being just x plus 3 times x plus 3, the only way we're going to get to the fourth power is squared. You could also do something like use substitution. That's basically what we just did there. Or you could do like your factors, like and do synthetic division to kind of figure that out. But x plus 3 cannot be broken down anymore. That's why they call it irreducible, right? So you could rewrite this as x squared, x cubed plus 5x minus 1 over x squared plus 3 squared. Okay. So we're going to do what we've been doing before. So we leave the left side as is. But we're going to write the right side as our first quadratic. Sorry, I think I just made that top too big. So we get x squared plus 3. And then we're going to add x squared plus 3 again, but this time it's going to be squared. Notice on the top here, we're still just going to have linear factors. So ax plus b, and then cx plus d. Because even though that looks like it could be the fourth power, which it is, it's still a quadratic factor, but it's just repeated. So now we're going to multiply both sides by the x squared plus 3 squared. So times x squared plus 3 squared. So the squared and that will cancel, times x squared plus 3 squared. Those will cancel. So we'll be left with x cubed plus 5x minus 1 equals ax plus b times x squared plus 3 plus cx plus d. Okay, let's multiply and combine like terms as needed. So ax cubed plus 3ax plus bx squared plus 3b plus cx plus d. Okay, let's get our like terms together. So ax cubed plus bx squared. I do have two x terms here, so I'm going to write 3a plus c times x. And then I have two constants, so 3b plus d. Okay, now it's setting our coefficients equal. So what's the number we could put in front of x cubed? We could put 1. So a equals 1. Okay, if we try to equivalate x squared to something on the other side, there's no x squared, so that means b has to be 0. Okay, so now we look at the x's, and we have 5 equals 3a plus c. Since I already know a, we might as well solve for c right now. 3 times 1 plus c. Subtract 3 from both sides, c equals 2. Last but not least, we've got our constant. So we've got -1 equals 3b plus d, but b was 0, so that's just 0. So d equals a -1. So now it's just plugging into what we have. So 1x, or we could just call that x, plus 0, so that's just x over x squared plus 3, plus c is 2x minus 1 over x squared plus 3 squared. Okay, one last one here. So on this one, the nice thing is we got that nasty denominator, but they're giving you what it breaks up into. Okay, so we've got this left side, but they're saying, hey, that bottom part really factors to x plus 2 times x squared plus 9. If you don't trust me, you can multiply it out and double check that, but I would just go with it if it's telling you that's the case. So this first one is a linear factor, so we put a constant on the top. And the second one is an irreducible quadratic, right? We can't break up x squared plus 9. There's nothing that multiplies to positive 9 and then adds to 0. So we're going to put a bx plus c on top, all over x squared plus 9. So we multiply both sides by the denominator. That cancels. This, when you multiply it, the x plus 2 will cancel, but you'll still have an x squared plus 9. On this one, the x plus 2 will not cancel, but the x squared plus 9 will. So you'll be left with 5x squared minus x plus 30 equals a times x squared plus 9 plus bx plus c times x plus 2. Okay, so now we're going to distribute and collect our like terms. So ax squared plus 9a plus bx squared plus 2bx plus cx plus 2c. Okay, let's keep going. So we've got 2x squared terms, so that's going to be an a plus b times x squared. I've got these two x terms, so we're going to have plus 2b plus c times x. And then we've got our two constants, 9a plus 2c. Okay, now we equivocate the coefficients on the left with what we got on the right. So the 5 times 5 equals a plus b. And then we've got, this is a negative 1, equals 2b plus c. And then last but not least, we've got 30 equals 9a plus 2c. Okay. How about I combine the first and second equation such that the b's will cancel? So I'm going to multiply this first one by a negative 2. So I have negative 10 equals negative 2a minus 2b. And the second equation I didn't change at all, so 2b plus c. Negative 11 equals negative 2a, that cancels, plus c. So now we're going to combine this red equation with the one that we currently have. So I think canceling out this c will be easier, so let's multiply it by negative 2 again. So I get positive 22 equals 4a minus 2c, and I'm going to rewrite this red equation below it. Okay, so I get 52 equals 13a. The c's cancel, so 52 divided by 13. A is equal to 4. Now that I have that, I'm going to plug it back into that green equation. So 5 equals 4 plus b. B equals 1. Then I'm going to use the blue equation. Negative 1 equals 2 times 1 plus c. Subtract 2 from both sides, c equals a negative 3. So our partial fraction decomposition will lead us to 4 over x plus 2 plus